Okie dokie. Okay, I guess we're all set. So we start with designing classifiers. And before we jump into different types of classifiers and how you want to design them, I'd like to go over some basic terminology as well as some of the ideas. And some of these things I might have done in the very first lecture. I don't remember that. All right. So maybe there are one or two things that might be repeated here. All right. So let's just recap what we mean by classification versus clustering. So when you think of building a classifier, basically you make an assumption that you have a collection of training examples. And every example looks something like this. There is a vector representing that particular example in terms of features and their respective values. And then there is a scalar quantity associated with that vector. And that scalar quantity could be simply 0 or 1 if you are talking of a binary classifier where you are talking of two classes. Or if you think of, for example, a problem where you want to read digits and look at the images of digits and classify them. So in that case, there are 10 possible answers. So the scalar in that case will be one of the numbers between 0 to 9, indicating the digit at hand. All right. So basically, this scalar component is what we call as a class label. And it need not be actually a scalar number. It could be, cat and dog. But ultimately, you will convert it into a 0 or 1 or some other number. All right. So you have a class label, and then you have a vector corresponding to that particular example. And that vector has certain values representing different attributes. All right. So if you have a situation like that, then we say we are performing, or when you build the model, you say your model is learning in a supervised mode. Because for every vector, there is an answer in the training example that is being given. You are telling the model, take this vector and give me this answer. So that's what we call as a learning with the teacher or supervised learning. In some cases, you might have simply a collection of vectors, no associated labels. So that is unsupervised learning. And typically in that situation, what you will do is you will take that collection of vectors and try to group them into certain number of meaningful groups. So that is what we mean by clustering, and that is unsupervised learning. A very simple example of classification. Say here you are given two sets of numbers. These are the measurements made for the height, let us say, all right? And these measurements are for two sets of players, female and male players for basketball. So what you see here is, of course, in this case, you have a measurement, 190, for example, and associated with that measurement is a letter saying F. So it indicates that, okay, we have one measurement, only one property that we are measuring. The value of that property for this particular example is 190, and this example represents a female player. All right. So like that, you have number of female examples, female players, and number of examples coming from male players. Now, suppose somebody says, all right, here is a height value that we have measured for a player, and this height value is 194. Can you classify this height value into a male player or a female player? That is what the classification problem is. And whatever mental model you will make for this particular example, that model will be your classification model. Only thing is, in practice, instead of getting just scalar numbers and a label, you get vectors and a label associated with those vectors. And these vectors typically are very high dimensional vectors. Clustering, as I said earlier, in this case, you don't have those male-female labels. Somebody has removed them. All you got is a set of height values, and you are asked to group them into, let us say, two groups. So you got to come up with some technique which will put them into two meaningful groups. So that will be what you call as clustering. Now, when you think of building different types of classifiers or different types of classification models, one could say, all right, you could be building what we call as a linear model or as a non-linear model. Linear model simply is a model that creates a classification surface which can be described in the form of a linear function or a linear relationship. A non-linear classifier obviously then uses some kind of non-linear surface. Obviously, non-linear classifiers are more powerful compared to the linear classifiers because majority of problems in real world cannot be solved nicely with linear classifiers. In general, you need some kind of non-linear classifier. Other distinction one can make, or a choice one can make when you are designing your classifier, is whether you want a one-shot classifier or you want a multi-stage classifier. A one-shot classifier is typically you input the data and it produces the output in one single calculation. A multi-stage means it's kind of tree structure. You look at some properties, make some partial decision, then look at some other properties, make further decision, and so on and so forth. So that will be what we call as a multi-stage classification. So in this example, you can see the distinction between linear and non-linear. So on the left-hand side, you can draw a nice line in 2 dimensions if you're working in a 2-dimensional problem to separate green circles from blue circles. In picture B, that's not possible. You need a non-linear boundary. In this case, the boundary is a circular boundary, all right, which is a non-linear boundary, all right? So that's what we mean by linear versus non-linear. This is an example of a multi-stage classification process. You are going through a series of simpler decisions to arrive at a final decision. In some instances, people talk of hard versus soft classification. Hard classification implies that the labels assigned to a document or object carry equal weight, all right? You're basically saying this is either digit 9 or you said this is digit 5. In soft classification, what you do is you don't say, okay, this is 5 or 9. You basically produce a result where different labels are given different weights. And you say, all right, the weight that this could be digit 9 is so much, the weight this could be digit 7 is so much, and so forth. The scheme that typically, or the logic that typically people use in soft classifiers is called fuzzy logic. And such classifiers are called fuzzy classifiers. We are not going to be talking about them. I just wanted to mention that term so that you are aware that there are classifiers that are called fuzzy classifiers. Most of the time, we will be looking at examples or discussions or talking about different classifiers in terms of binary classification problems. But in practice, you end up with classification problems where you don't have to decide between 2 classes, but you have to decide between M classes, where M could be any number, 5, 10, 20, even 100, all right? So those classifiers are what we call as multi-way classifiers. People generally do talk about only 2 class classifiers or binary classifiers for all the theoretical and other explanations. with the reason that any multi-classifier problem can be solved using a collection of binary classifiers. For example, if you want to have a 3-class problem, so you can divide that 3-class problem, say A, B, and C are 3 classes. So you could make it A versus B and C. So that's a binary problem. Then B versus C and A, that becomes another binary problem. And then C versus A and B becomes another binary problem. So any M-class problem can be solved using a series of binary classifiers. So that's why when people study properties of different classifiers, talk about theory, most of the time they are limiting themselves to a binary classifier. That doesn't mean that those methods do not apply to multiple classes. It's just the way we want to do things. Okay. There is another interesting variation, which is called single versus multi-level classification. Typically, when you get an input vector and you need to classify that vector, basically you will be generating a single class label for that vector. That is what majority of classification models do. But in some instances, you might be even interested in generating multiple labels for a given input vector. And there are certain applications where you might need this kind of classification model. To give you an example, let's say you're looking at a news story. The news story could be dealing with politics in the sports. So in a way, it is a sports story because it's talking of sports. But on the other hand, it is also a story about politics. So basically, there are 2 potential labels that are possible. So in many applications, people want to get number of labels assigned to a given input because that's how they have designed their application. So such situations need what we call as a multi-label classifiers or multi-label classification. And again, such classifiers are, in general, some variations on your basic classifiers. All right. So that was about different types of classifiers. All right. Now one might say, all right, we got different types of classifiers. What kind of underlying algorithm or technique is involved in such classifier, in a given classifier? All right. So from that perspective, if you want to differentiate between different classifiers, you can say, all right, we have a classifier which we can classify as a generative classifier, or a classifier could be classified as a discriminative classifier, or it could be classified as a geometric classifier. Or our model is a generative model, discriminative model, or a geometric model. In a generative model, we assume that the data that we are looking at and trying to classify is coming as a result of some mathematical generative process, which can be described in terms of probability density functions and a priori probabilities and all that. That is, one takes a full probabilistic approach. For example, you might say that data is coming from a Gaussian distribution. All right. So if you build a classifier using that kind of understanding, then you end up with techniques that are totally 100% based in statistics. And one such model is basically, Bayesian classifier or using the Bayes rule. In discriminative models, what we do is we don't really assume much about the density function or probability distributions and all that. We directly try to estimate what is the posteriori probability of a given input coming from a particular class. So those models directly try to map input to class labels. And in geometric models, what we try to do is we try to look at the problem from a geometric point of view and try to learn some kind of geometric function that will allow us to create a surface or a decision boundary that will separate examples from different classes. So these are the underlying approaches that people follow, one or the other. And depending upon somebody's liking, they might follow the first approach, somebody might follow the second approach, somebody might follow the geometric approach. So those are all different ways of building classification models. Now what we'll do is we'll walk through a very simple example that should give you the complete picture of what is totally involved in building a classification model. All right. So we will build a classification model, and you can think of this model as a smartphone app that you want to build. All right. The app has a very limited capability. You basically want it to differentiate between two types of flowers. So one is the iris virginica, another is the iris versicolor. So you want to take a picture with your smartphone, and then the app that you have built for classification will tell you whether it's an iris virginica or iris versicolor. All right. So in order to do this, first thing we need to do is to collect a large number of both types of flowers. Now, if you are not capable of making a distinction between these two types of classifiers, obviously you will need an expert, somebody who is knowledgeable, who can tell you, okay, this is iris virginica, this is the other kind. All right. So basically you have an expert, you're collecting data, and then expert is assigning labels to this data. So you collected, let us say 100 flowers, and then expert says, okay, these flowers are of type 1, and these flowers are other type. All right. So basically, with the help of an expert, you are collecting a large number of examples and labeling them. All right. And of course, in order to do the classification or build your model, what you need is you need some kind of properties to be measured so that those properties can be used in your classification model. So in this case, you decide that, okay, you are going to measure petal area and sepal area as two properties. All right. How we will do that? Let's leave that for anybody who wants to do image processing, because one can write some image processing techniques, routines to filter, to figure out where the sepal and the petals are and how to calculate their area. It's possible, it's doable, people do it. All right, so, but let's not worry, okay? So let us assume that that's possible and we have done that. So at the end of this process, what you have is a collection of examples. Every example has two attributes or two features, which are the petal and sepal areas. And then there is a third component associated with every example. And that third component identifies whether that example is of flower type A or flower type B. All right. So that becomes your training data. And as I mentioned earlier, the first thing you want to do is to do the visualization. All right. So in this case, since you have only two features, so you basically map the data in 2 dimensions. And in order to make a distinction between whether particular example is coming from class A or class B, what you do is you basically plot them with different colors. So essentially, you can see here, we have plotted our examples in 2 dimensions. And we have given a red color to all the measurements that came from versicolor flower. and the other color is for Virginica. All right. And of course, in this case, we have only 2 dimensions. All right. So basically, everything that you can think of about this problem is present in this graph. All right. Now, our objective is to build a model that can separate Virginica from versicolor. All right. And to do that, it has to rely on only these 2 features that we have measured. All right. So if you look at this chart or this graph, you can say, all right, I can draw a line as shown here. And this line is pretty good at separating almost all the examples. It's not 100%, but fairly good. All right. Most of the blue dots are above the line, and most of the red dots are below the line. And there are 3 or 4 or 5 points that are not in correct position with respect to the line, but otherwise this line is fairly good to separate. All right. So this line is your classification model. And mathematically, what you can do is you can write the equation of the line. And given an input example, you can figure out through simple geometry or through simple equations whether that point is above the line or below the line, or that point is sitting on the line. All right. So basically, that's your classification model, and you should be happy that you're able to get that very quickly. Obviously, this doesn't happen in practice because in real life, you're not working in 2 dimensions, you're working in a much higher dimension. All right. But before we move on, let's say that you say, well, the line did make some errors. So how about if I, instead of using a linear boundary, let me use something little different, use a nonlinear boundary that is mostly flat, then it turns up, stays flat, goes down, again is flat little bit, and then turns up, and then stays flat. All right. And with this, I am able to basically reduce the errors. So I can see that with this boundary, only 1 blue point is getting misclassified. Everything else is working nicely. All right. Then your friend sees that boundary and says, well, I can do better. Let me make a nonlinear boundary, which is a little more curvy, all right, which possibly requires a higher order polynomial equation to describe. But this boundary is damn good. It does not misclassify anything, all right. So you can say that for your given problem, you have number of possibilities in terms of your classification model, all right. So now the question is, given these 3 possibilities, which one are you going to pick if you were the one who was going to decide whether I should pick the first model or the second model or the third model? Yes, please. First. Everybody agrees that first model should be picked up?
It depends on what your criteria is. If your criteria is precision or, getting it correct, then I pick the third one. If you want probably speed, then you want the first one.
Couldn't you have problem with sitting though? Yeah, that's the problem.
Okay. Let me answer that question. Okay. Obviously, the third model is giving you 100%. All right. But you have to remember, this model is giving you 100% on this collection of examples that you have. All right. But your system is supposed to work not only on these examples, but it's supposed to work on any other example that might come from those 2 flowers. And there is no guarantee that all the other examples that you will get will behave so nicely that they will basically be happy with this boundary. All right. So in some sense, the third boundary, which is highly nonlinear, is what we call as an overfitting. You are basically tuning that boundary to your training set, all right? And you do not know how well this will do with examples that it is likely to come across in future, all right? Same thing can be said for the second thing. Although second one is not that much of overfitting, but still it is overfitting. So out of these three choices, the choice we will be making will be the first one, which is the linear boundary, all right? But this gives you an idea of how we go about building the models and selecting them, all right? So one can talk here of model complexity, whether you want to select a simple model or you want to select a complex model, and how do you decide about that? So in practice, what people do is you want to avoid overfitting. That's number one criterion, because if you can avoid overfitting, then hopefully you can get the model which is most appropriate for your situation, all right? So to do that, typically what people do is they take the entire collection of examples that you have at your disposal to build your model. And what you do is, out of that collection, typically you take about 70% of the examples and use them for training or for building the model. So if you have 1,000 examples, you will keep aside 700 examples and you'll say, okay, these are the examples I'm going to use to build my model. Okay. Then out of remaining 300 examples, you might say, well, I'm going to keep 150 examples for the argument's sake, or 100 examples for what we call as a validation set. And the remaining examples we will keep for test set, all right? So let's look at the test set first, and then we'll talk about the validation set. So you have training examples, which you will use to build your classifier. Then you have test examples. These test examples are examples that classifier hasn't seen during the training process. So when we present these test examples to the classifier, if classifier does well on these test examples, then you can say, well, the classifier or the model that we have built is a good model. It is just like I give you assignment number 1, I give you 5 exercises, all of you do it well. If somebody makes an error, I tell them that's the error you made, and you get all those 5 exercises correctly. And then next day I have an exam and I give you the same examples in the exam. Obviously, everybody will do well, but that doesn't prove that all of you have learned those concepts. So for the exam, I have to give you something different. Same idea applies here. So while building the training, or making the system learn, we have one collection of examples, which is a very large number of examples. Then to check whether the system has learned nicely or properly or not, then we have some test cases that we run through. And if it does well on those test examples, we say, well, our system has learned well. All right. So that's the reason you want to divide your training data, your collection at your disposal, into training set and then test set. What about the validation set? It turns out that many of the algorithms that one ends up using for building the models, those algorithms have number of parameters that are involved. And the performance of the resulting model is a function of those parameters also. So sometimes you want to make sure that you are choosing those parameters very wisely and appropriately and correctly. So validation set is a collection of examples that you typically use to fine-tune the parameters that your system is going to have at the end. So you have training, which does bulk of the training, then model might need little fine tuning. So you do that fine tuning using validation set, and then you throw the test set to figure out how good is your model. So this is typically how you will basically build your models, whether you're building them for classification or building them for regression. So any supervised learning situation, this is what you will be doing. All right. So if you look at the overall process of model building, this picture kind of shows you the process. So you have a data set, and basically you divide that data set into training set and test set. And then you go through the training of the model, you do the evaluation, and you use parameter settings, etc., etc. All right. There is one term that I haven't mentioned, and that is cross-validation, that you see as a new term appearing in this picture. All right. So let us see what we mean by cross-validation. Once you have decided, okay, here is our collection, and what we want to do is we are going to do the test set, validation set, and training set. All right. Typically, again, to make sure that the model that you're building is really good and it's not going to be performing poorly when you put it outside in the real world, what you do is you go through a process of what we call as an n-fold cross-validation. So going back to our 1,000 examples that I mentioned earlier. So if you are doing cross-fold validation, the basic idea is that you divide your entire set. For example, 1,000 examples, you divide them into 10 sets of 100 examples each. And out of those 100 examples, sets of 100 examples each, you take first 100 examples and say, all right, these examples are going to be my test examples. You take another 100 and you say, these are going to be my validation examples. And the remaining 800, you say, these are my training examples. So you do that. And you train a model, build it, and go through the process. And then what you do is you come back and say, all right, what I'm going to do next is I'm going to make my second set of 100 examples as my test set, third set of 100 examples as my validation set, and remaining examples as my training set. And again, I'll repeat the process. So basically, the idea of n-fold cross-validation is that you rotate groups of examples as training, as test, or as validation. So basically, you are creating situations where the model is going through varieties of scenarios. And then whatever you end up, that tells you, okay, here is a good model. So if you are building a model and through this process, you find that the model performance is more or less very similar every time, that means your model is not tuned to a particular collection of training examples. It's fairly general enough. And you can then, go ahead and work with it. On the other hand, if you find that your model shows much high accuracy for certain collection of training examples, and it shows poor accuracy when you go through this cross-fold validation and run it again with another set and all. That means the model accuracy is varying quite a bit when you run this experiment. That means in that case, you really need to look into the nature of the model you are using to see whether that is the correct model you're using or you need to do something different. All right. So this is what we call as n-fold cross-validation. And in certain situations, you may not have that many examples to do the model building. Suppose you have only 50 examples. In that case, it doesn't make sense to divide those 50 examples into 10 groups and then do this. So in such cases, typically what people will do is they will take one example as a test and remaining examples as your training examples and repeat this process 50 times. Okay. So that is what we call as a leave one out method. All right. Again, leave one out is an extreme case of cross-validation. But in general, we talk of n-fold cross-validation. Okay, so next question is, all right, how do we measure the performance? How do we say whether this particular model is better than the other model? All right. So classifier performance, again, I'm showing you in 2 dimensions for a binary situation here, all right. So let us say that you have an example whose correct category is class C1, and your classifier also predicts that it is class C1. All right. So basically, you are looking at the cell that is marked as an A. All right. Maybe the correct category is C2, but your classifier says, no, it is class C1. So that is what is cell B is representing. And similarly, cell C and D are representing. All right. So basically, with a binary classifier, you have 4 possibilities. You know, the class is 1, it says class 1, class is 2, it says class 2, and other 2 possibilities are where it's class is 1, it says 2, or vice versa. All right. So what one can do is one can define the accuracy as A plus B, A plus D, because those are the cells where the correct decision has been made. All right. Divided by sum of all the results. So that will be A plus B plus C plus D. All right. So that tells you, okay, my classifier is 70% accurate or 80% accurate. All right. Sometimes you may want to use precision and recall idea, which I mentioned in the last lecture. All right. So when you want to talk of precision and recall, you have to define precision and recall with respect to class labels. So you can say, all right, for class 1, the precision is given by A divided by A plus B. And precision for class C2 is given by D divided by C plus D. And similarly, you can define the recall for class 1 and recall for class 2. Okay. Many cases, you will come across terms like true positive, true negative, false negative, false positive. Okay. Again, these terms represent what we saw in the last slide. True positive is when a class is correctly identified. It was C1 and the system said it is C1. Okay. It's a cat and system says it's cat. So that's true positive. All right. True negative, correctly identified as not relevant. All right. So basically, that's what it means. All right. False positive means when you make a mistake. All right. So incorrectly labeled as relevant. It was a dog, but you said it's a picture of a cat. All right. So that's basically all right. So one can talk of true positive, true negative, false positive, false negative. And in certain fields, these terms are more popular than the precision and recall or accuracy. If you are doing any classification study or model building for a medical application, in the field of medicine, people like to use the terms true positive, false positive, true negative, false negative. All right, when somebody has a particular serious disease and whether identified correctly or you misidentify it. So that's how you will define true positive, true negative, and so on and so on. Another thing sometimes people do is, especially again in medicine and defense related applications, People like to know what is the ROC characteristic of your model and how does the AUC, area under the ROC curve, looks like. These are some of the numbers that people in defense and in healthcare really like to talk about. All right. So if you look at our what we defined earlier as a true positive rate, all right, so instead of talking in terms of class 1 or class 2, let's say that true positive rate basically is given by A divided by A plus C, assuming class 1 is our positive class, all right, and a false positive rate is given by B divided by B plus D, all right. Now, typically what happens is that in majority of these classifiers, as I said, there are certain parameters. And if you change some of them, obviously the performance changes, all right? So if you have a particular parameter, let's call that parameter as a threshold parameter, which is finally a parameter that gets involved in making the final decision, all right? So if we change that parameter a little bit, it's a kind of slider, you move it left or right. What happens is that change in the threshold value changes what is your then true positive rate or true false positive rate. So if you make a plot of how sensitive your rates are with respect to this parameter that you are manipulating, then that plot is what we call as an ROC curve. And then using that plot, you can calculate the area under the curve, all right? And typically, these numbers and these plots are what people in medicine and the defense industry really like, because that's how they have basically dealt with the systems in the past. So they want to make sure that whatever you are proposing has better numbers than the system they are using, and those numbers are being quantified in terms of these characteristics, right? For M classes, similar to what we shown you earlier, you can create a big matrix, which is typically called a confusion matrix, all right? So basically in the confusion matrix, all the diagonal elements correspond to the cases where the correct decision is being made, and all the non-diagonal elements will indicate where the mistakes are being made. And those non-diagonal element locations will tell you what kind of mistakes are being made. So for multi-class problems, it's pretty typical, pretty standard to create a confusion matrix to show the results. And especially if you are studying a problem and you look at the confusion matrix, you might say, well, my system is getting confused with the 2s and 5s. So how do I, bring in some more features so that it can differentiate between those two classes much better than what it is doing, all right? So it kind of gives you an idea of where the weaknesses are and how you could possibly improve those weaknesses. Now, I defined the accuracy earlier, all right? That is number of classes, examples that are correctly classified divided by the total number of examples. Now, it turns out that accuracy measure could be a misleading measure. If the classes are present in a more or less equal proportion, for example, you're looking at classification of 100 examples or 100 test cases. And in those 100 test cases, you have examples from two classes, and they are more or less 50-50 or maybe 52-48 or 55-45. In that situation, accuracy makes sense. But if one class has 80 examples or 90 examples and another class has only 10 or 20 examples, then accuracy really doesn't make any sense. Because if I have 90 examples from one class and 10 examples from another class, I can get 90% accuracy by saying every time it's a class 1. and I will be true 90% of the time. All right, so that doesn't really make any sense. So typically in situations like that, you don't want to talk of accuracy, you want to talk of precision and recall with respect to each class. So you can say, all right, for class 1, this is the value of the precision I'm getting. For class 2, this is the value of precision I'm getting. All right. So that is a better way of doing things in those cases. All right. Now, so far I mentioned errors, etc. about classification models. Before we move on, just very quickly, 1 or 2 slides, I want to mention how do you measure error in the case of regression. So in regression, basically, you're trying to fit some kind of curve, all right? So you can say I can measure the regression error as a sum of squares error. So basically, I have a collection of training examples. I have fitted a model, in this case, a line or a curve or surface. Then how far my training points are lying from this curve. If I measure that difference vertically down or vertically up, then that difference gives me an idea of how good is our model. So what we can do is we can square up those distances and then add them up. And that gives us a good indicator for how good is our model for regression. Bias and variance are the other 2 terms which you are likely to come across. So bias means expected difference between model prediction and truth. Obviously, a model is not going to be 100% accurate. All right. So question is, what is the expected difference between the prediction and truth? Some models might be more optimistic. So they're always giving you a more hopeful answer, let us put it that way. Some models might be pessimistic. So there might be a difference in the prediction, and this difference is easier to understand if you look at the regression problem where you're trying to predict some number. So you might have a very optimistic estimate and your estimate is higher than the actual number, or you might have a model which is always pessimistic and the number produced by that model is little lower than the actual thing. All right. So that is what we mean by bias, whether your model is overly optimistic or pessimistic. Variance is how much the model differs among training sets. Remember, I mentioned you do the n-fold cross validation. So if your model is producing highly variable results, the accuracy is going from 60 to 70, 75%, that means your model has a lot of variance. On the other hand, if your accuracy is remaining between 70 plus minus 1 or 2%, that means your model has a very low variance. So one can talk of models in terms of their variance as well as in terms of their biases. So high bias models makes inaccurate prediction on training data. High variance model does not generalize well to new data sets. Low bias models make accurate predictions on training data, and low variance models generalize to new data sets. All right. So basically what you should be doing is you should be going for models that have low bias and low variance. All right. That way, anything that you get is likely to be very useful and do a good job when you deploy it for an actual application. All right. So there is a final slide here to end this particular discussion. And this is what we call as the guiding principle for model selection, known as Occam's razor. To put it in a very simple way, what you should be striving for when you're building a model is to keep it simple. Go for a simple model as far as possible. Okay, those models are in the long run, they do a good job, they do pretty good, and they are useful. Highly complicated models are likely to fail at some point. Okay, so that's basically our brief discussion about some basics related to classifiers, how to go about designing classifiers, what are the choices you should be making, and things of that nature. Okay. So with that, what I'm going to do is I'm going to start talking about our first classifier. All right.